Hi, everyone. In this video, we are going to look at greedy algorithms 1. Greedy algorithms are used to solve optimization problems. Earlier, last week, we have seen that, including this week, right? And so we have seen how to use dynamic programming to solve optimization problems. And as a matter of fact, dynamic programming is a really powerful technique because it can also solve any problem whose solutions can be expressed as solving a recurrence relation following the divide and conquer principle. So what that means is that to solve a optimization problem or a problem with the current parameters, if we can break the problem into several subproblems with smaller parameters, and then when we solve these subproblems, then we will be able to solve the original problems through the recurrence relation. So then we can iteratively solve the problem. So the general technique is to use memoization with recursive calls. So programming is easy there. The only difficulty is to come up with a recurrence relation. So we talk about the general technique that we first formulate the problem by creating a name to represent the problem, and then specifying the parameters. And then we'll look at, in order to solve the problem for the current parameter, then we can figure out what subproblems do we need to solve, right? So that is the second part of it. So that part I call localization. So we got the formulation, and then we have a localization. Combine these two, we got a recurrence relation, and then we can directly use the memoization technique. So that's dynamic programming. Okay. And obviously, we can also get rid of recursive calls by starting from the bottom up, which means that we solve the lowest level of subproblems first, and then we move on to the higher level, and then move up to the higher level, and so on. Okay, until we reach the level for the current parameters, or for the original parameters. So today we're going to look at greedy strategy. So greedy strategy is used to solve optimization problems. So by greedy, it simply means that instead of looking at a recurrence relation, sometimes it is possible just to use one strategy. So which means that we don't need to look at several subproblems. We only need to look at one. So that one subproblem is the one we are looking at. So then solving that subproblem, then we can solve the original problem. Then again, recursively, in order to solve that subproblem, then we're going to solve another subproblems, but it will be depending on just one. Hence, greedy algorithms are often very straightforward to code, but we need to prove that your greedy choice or your greedy strategy actually will provide you with the optimal solution. So by optimal, we mean either minimization or maximization. Okay, again, as before, we're going to look at examples. And then from that example, then we can see what this greedy strategy algorithm will look like. So the example we're looking at is activity selection. Suppose we have the following input, which is a set of activities. So we're going to write it as A1 to AN. So we have N activities. And each activity is represented by a start time and a finish time. We can represent it as a pair. And let's say these activities will take place in the same room, okay, classroom, for instance. Then we want to make sure that two activities they don't overlap. So their start time and finish time, they don't overlap, so that so at each time that in that room there is only one activity taking place there. Okay, so for instance, if you have a activity, let's say I start at 8 and then ends at 9, the other one starts at 9 and then ends at 10. So these two, they can occupy the same room without any overlap. So there is no conflicts. Then we are going to say that they are compatible. And on the other hand, if you have an activity, let's say this activity is a class, starts at 8 and then it ends at 9:30, and then there's another class that starts at 9, but it ends at 10, then these two are not compatible because that there is a 30-minute overlap for these two activities. All right. So now we have N activities, and each activity is represented by a pair of start time and finish time. So what we want to know, right? So let's say this is a classroom, and you have these activities. We want to figure out the maximum number of activities that we can hold in this room. Okay, so that is the output. A maximum size subset of mutually compatible activities. So the maximum number, right? So this is a maximization problem. So now let's make it concrete. So we're going to have the following input. So this is the input. So we're going to have 11 activities. And so the start time and finish time for each activity is given. And for instance, here, for activity 1, it starts at 1 and it ends at 4. And for activity 2, it starts at 3 and ends at 5. We want to find the maximum number of activities that can be completed in the same room. So for instance, here, A3, let's see, 8, the activity 3, and 9, activity 9, and 11, they are compatible. So activity 3 starts at 0, ends at 6. Activity 9 starts at 8 and ends at 12, and activity 11 starts at 12 and ends at 14. So if you look at the timeline, say this is the time, you have, it starts, let's say this is a 0, so then it starts 0 and then 6, and then here is 8, and then 12, and then 12, and then 14. So they don't overlap. But this is not a maximum because we can find another set of activities. In this time, we can say, for this, instead of selecting 3 to begin with, we can select uh, 1. So that starts at 1, and then it ends at 4. And the other one is starts at 5 and ends at 7. So this it's not proportional. So let me make it more, make it redraw so that it's proportional. So this is about 4. So it's about 4 like this. And so this will be 1. This will be 4. And then this will be 5. And this will be 7. And this 0. Okay. And as a matter of fact, so this is going to be maximum. All right. But we also know that maximal solutions may not be unique. For instance, we could have another here. So they are different, but they are also so the second one also has 4 activities. Second choice also has 4 activities. So that's what we got from this example. So then our goal is to figure out an algorithm or a strategy to first determine the maximal solution. All right. So this is just the diagram to visualize the solution. So this is a feasible solution, right? So any solution is feasible if they satisfy the requirement. So this is feasible, but not optimal, or in our case, but not maximal. And next one. Okay, so this is also feasible, as you can see. So this is the finish time. This is the end time. So this is the finish times, a start time, right? So this is finish time, start time, finish time, and start time. So they don't overlap. So as long as the finish time before is less than or equal to the start time of the another one, then these two are feasible. So these two are compatible. Right? So we just want to find the maximum number of such pairs. Now let's do a little analysis. First of all, to make things easier, we are going to sort the activities based on finish time in increasing order. Okay, we sort them so that we can still name the first one depending on the finish time. So we just name them. So the first one has the earliest finish time. The second one has the second finish time, and so on. And then we are going to look at, for any ij, okay, all the activities that are compatible in this set. Okay, so which means that for any ij, so it's going to be a set of all activities, ak, such that fi is less than or equal to sk. So which means that we're going to look at activity I, look at activity j. Now for AI, it has si and it has fi. For aj, it has sj and fj. Now this is timeline, but this ij, so this sj can actually be smaller than fi. But in this case, in general, we're just going to say that for any ij, we're going to look for or ak. So this k including j so this K could go to J such that they are compatible. So which means that we are going to have, say, if this is compatible, then we are going to, it has to be in between. And if Sj is greater than Fi, then this is obviously you don't have AK in between. And even in this case, you may not have AK in between if this condition is not met. So which means that for this Sij is all the compatible activities with AI and AJ. Now, similar to solving any problem using divide and conquer. So we are going to first look at how we can solve this using dynamic programming, and then we're going to proceed to figure out whether we have an easier selection of subproblems. So first, let's look at formulation. So which means we're going to name the problem. And so since we're going to find out the size or the maximum number of optimal solutions, so usually we can either use the cost or use the profit. And depending on which angle you're looking at things. So let's just say, okay, let's Cij, so it's just a name, but we specify, the important part here is that we specify the parameters. So parameter here is I and j. So let Cij denote the size of an optimal solution for Sij, and then since the given set of activities is from 1 to n, so what we end up solving is C1n. So when we solve it, then we solve the problem. So we're going to figure out which one we're going to select AK. So that AK, by selecting it, for instance, I have AI, I have AJ, and I have AK. So when we're selecting it, we essentially break the timeline into 2 parts. So this timeline here, we're going to start from the end time. Right? So there will be Fk, that's the end time. And then we want to know these 2 parts, it's optimal. Once it's optimal, then so then since we select AK, so we have AK, so we got SK, we got K. So what we want to know is that starting from, so we want to know, you think about Sij, so we got a K in between, so which means that I'm going to look at I to K. So which means all the activities compatible with I and K. And then there's another one. Also, all the activities in this portion. So all the activities. So this is AI. Let's say all the activity here that's compatible with AI and AK. And then all the compatible problem activities here that's compatible with AK and AJ. Okay, so AJ has a start time. So then both of them we want them to be maximum. And since we already select K, so we gotta add 1. So which means that the recurrence relation is when there are activities in Sij. So what we want to do is to pick a K from it. So pick a activities, AK from it, such that this is a problem and this is a problem. which is the optimal solution for that subproblem, and add 1. So add both of them and add 1, because this one is from the one we select, AK, and then we want this K to reach the maximum. Okay, so that's what it is. If Sij is empty, then you don't have any solution there, so this is equal to 0. As we look at as we discussed when we look at our dynamic programming, so it's easy to figure out the running time. The runtime is to look for how many subproblems we have. So first we look at Ij. Right? So we know that J will have to be greater than I, but then for I, it starts from 1 to, let's say, n minus 1. So J could start from 2 to n. So you have these many pairs. So for 1, you can do this, you can do that. So you can consider all of those. So there are n squared, the order of n squared, many. Okay, so in other words, you have, so for 1, you have n minus 1 choice. For 2, for this row, you got n minus 2. So you add them up. For n minus 1, you only have 1 choice. So you add them up. So this is, we know this is equal to this. So that is in the order of n squared, many pairs Ij. And then for this K, so if it's not empty, then you would have J minus I plus 1 choices, and then obviously they will be less than n. So you are not going to exceed n cubed. So which means the running time is at most n cubed. So that's dynamic programming. Now let's figure out whether for this particular problem we can have a better strategy to select a subproblem so that we don't have to look at all possible AK in Sij. So now what we want to do is, now you look at this, right? So we assume F1 less than or equal to F2, and then less than or equal to Fn. Because this F1 is the smallest, obviously, after sorting, and this is the first one we should select because it will not. So this is the obvious choice. We start from the early finish time. Okay, so once we pick this, then we're going to look at S2. So if S2 is less than F1, then A2 cannot be selected. So the one we can select after this is to find the first one. So to find the first one, whose start time is greater than F1. Okay, so that means we are going to find the first one or the smallest. The first one means the smallest J, let's call it I, such that Si is greater than or equal to F1. And likewise, and for S, after this Si is, so after AI is picked, then it has Fi. And then we want to find the smallest J, such that Sj is greater than or equal to Fi. So then the start time of the next activity you select must be at least the finish time of the previous activity you select. So that way we can have a feasible solution. Okay, so to formulate this idea, so now we're going to let SK be all the activities SI such that all the activity AI such that the start time of that activity is at least the finish time of K. Okay, then we're going to show that selecting such activity. So selecting the activity in the way I just described actually provides an optimal solution. Okay. So in order to show this, then we want to show the following result, which says that suppose this activity AM in SK has the earliest finish time, then for any optimal solution you can have, for any maximum solution you can have for SK, we can always find, okay, we can always find another optimal solution such that AM is in that solution. Okay, so which means that, so the idea is this, we just need to find one optimal solution. Let's say you have a optimal solution. So let's usually we say, let's call it the pi star is the optimal solution. And then let's say, so for IJ, for K, okay, no longer IJ because we look at linear. Okay, suppose AM has the earliest finish time, but AM is not in it. Okay, then we are going to, for this optimal solution, there must be, let's call it AM prime. So that has the earliest finish time, right? So this exists. Then, because they all come from the same set, so AM in SK, AM prime is also in SK, and then we know AM has the earliest finish time, and then AM prime has the earliest finish time in this solution. I can always replace AM prime with AM. Replace AM prime with AM. So this is, again, is a feasible solution because this is optimal. So then this new solution is also optimal. So if you want to draw, it's obvious, it's pretty obvious. Let's say this activity Fm prime is the smallest in this solution, but AM is not in it. But we know Fm is smaller than or equal to Fm prime because we assume that Fm is the smallest is in AK, so we can replace Sm prime with Sn to come up with another solution. They have the same number of activities, and since we begin with a optimal solution or maximum solution, the new solution is also optimal. So this proves, so this is a proof that shows that greedy choice provides the optimal solution. Greedy choice works. Works means that not only it provides a feasible solution, but it provides an optimal solution. So this is a visualization of greedy choice by selecting activities with the earliest finish time. So we look at the earliest finish time in the example. So we just do a scan. Okay. So this activity has the earliest finish time. So that's the one we are going to pick. And then we are going to scan to the next one. So this is the next one, but then the finish time overlap with the, I'm sorry, the start time overlap with the finish time of the previous choice. So we go to the other one. This is the same thing. And then we go to the other one. And then this time, so this, okay, so we can select this. So that's what we're going to have. So we're just going to select it. So similarly, we're going to look at this. We keep sweeping. We look at this to see which start time doesn't overlap with the finish time. So this is will be this one. All right. And then once we have done that, then we're going to look at which activity will have a start time that doesn't overlap with the finish time. In this case, it will be the last one. All right, so that is a, this is a greedy algorithm, and we already shown that this is optimal. Coding greedy algorithm is straightforward because the selection is easy. There is no, well, it's a recurrence relation, but the recurrence relation, it only, you only need to figure out one subproblem. From there, you figure out another subproblem. So that's a linear, rather than a problem depends on more than one subproblems. It only depends on one. In this activity selection problem, so we first need to sort the finish time, and that in general would take n log n time. So after that, it will be linear, right? So this is n log n for sorting, and then selection is linear. So selection or greedy selection is linear. So this is sorted. So add them up. So this is still big theta of n log n. Compared to dynamic programming, that requires, that runs in qubit time, cubical time. So this runs in linear time.